All right. Well, good morning, and this is the wrong slide deck. We want eighth week Wednesday. All right, and so we will continue talking about numeric optimization. So on Monday we talked about coordinate descent, and that's a pretty good algorithm for finding the optimum, or at least a local minimum for a multi-dimensional function, and you have that in your homework. Another algorithm that works well is the nelder-mead algorithm. This is actually the algorithm that is the default optimization algorithm that gets used in R's optimization function. So R has a built-in function called optim, and it will locate a local minimum for a function that you give it. And its default algorithm is the nelder-mead algorithm. You can actually use other algorithms too. You can use basically things that are based on gradient descent, and those also exist in optim. But anyway, nelder-mead, it's an important algorithm. So let's take a look. All right, so the nelder-mead method. A lot of my notes are based off of Dr. Gavin's notes from Duke. This is what we call a direct search method, meaning there is kind of no use of derivatives or anything like that, and the way it searches is it basically, you give it a starting kind of location, and it kind of sends out little feelers, right? So you start here and it says, okay, what value would I get if I travel in this direction? What value would I get if I travel in this direction? And kind of using that, it decides where to investigate next. All right, and so it has kind of this set of instructions, or the algorithm, to decide where to look for next and in which direction to move. Okay, it works very well, but it is not guaranteed to converge. So a lot of these methods that we learn and stuff, they all kind of have this problem of not being guaranteed to converge. But yeah, it works well. So at the heart of the algorithm, the nelder-mead method uses what's called a simplex. Okay, a simplex is basically a shape that has one more vertice than there are dimensions. So if your function is a function of two dimensions, okay, then the simplex is basically a shape that has one more vertice, so it would be a triangle. Right? If your function exists in three dimensions, then you have a shape, a simplex, that exists in three dimensions but with four vertices, and that is a tetrahedron. Okay, and for like a four-dimensional function, your shape exists in four dimensions but it has five vertices. That's called a five-cell pentachoron. It's kind of this. It's I don't know. It's hard to imagine things in four dimensions, but this is kind of this is what it looks like when you rotate a five-cell in four-dimensional space, and when it unfolds. But anyway, that's kind of the idea here. So in the slide examples, we're going to look at a two-dimensional function, and I use contour plots to indicate like where the local minimum would be on the contour plot, and we will see a triangle, being our simplex, kind of move around inside that plot. Okay, and so anyway, we have some kind of function that exists in this two-dimensional space, and we want to find a local minimum. And so we start our starting location is technically three starting locations. So we have to kind of define a starting triangle, starting simplex, and in say R, if you were to use the optim function, you just give it 1 point as its kind of starting location, and then it kind of makes up other other locations for its the starting simplex. And the way the algorithm runs is it does these kind of, it tries out one or multiple of these steps. Well, number one, it sorts it, and then it will always check convergence. So steps 1 and 6, it will always do. And it might do, between steps 2, 3, 4, and 5, it might do one or multiple of those things. So it will first try a reflection, and then it might try an extension, it might try contraction, and it might shrink down. So let's take a look at each of these things. All right. So the first thing that it needs to do is it starts off with our simplex, and it evaluates the function at all 3 places. So it's going to, you have, your 3 corners, which we will call U, V, W, and they are sorted. The corners are sorted or labeled in such a way that U is currently the value that produces the minimum, okay? And W is the value that produces the maximum. So we evaluate the function at these 3 locations, and we label, the value that has the highest value, our W, the value that has the lowest, our U. Okay, so U is our best performing point right now, and W is our worst performing point. And the first thing we do is we try doing a reflection. Okay, so we take that worst point W, and we reflect it through the centroid of the 2 remaining points. Okay, so U and V perform better than W, and so we look at this line U and V, and we reflect W through that point. Okay, and so this gives us our point R. So basically, you would evaluate, how do you reflect this? You find the midpoint of U and V, and then you find the vector that connects W to the midpoint, and you basically add that same vector to the midpoint, and that will take you to the reflected location. And you are going to evaluate the function, our 2-dimensional function, at the reflected location. And if this point is better than V, but not better than U, we will go ahead and replace W with R. And so this will be the next simplex that we will have, okay? So if R is better than V, but not better than U, then we will use this triangle, and V will now be our worst performing point, okay? So that's what we will have for the next one, okay? And then we would go ahead and just skip to the end and check for convergence, okay? On the other hand, if the reflected point is even better than U, okay? So if the reflected point is better than U, okay, then what we do is we say, well, you know what? We seem to be moving in the correct direction. So let's just press our luck a little bit, and let's go even farther out. So we go to, we check an extended point, okay? So if the cost of the reflected point at R is better than the cost at U, then we extend this reflected point even further to E. And if we will evaluate the function at location E, and decide what to do there, okay? So basically, again, the way this is going to work is first we calculate the midpoint between U and V. You would have kind of a vector connecting W to the midpoint, and then basically we add double that vector, right? So we add, if you take this vector from W to, say, M here, and you add that to M, you'd get to R. And if you add that same vector again, you'd end up at E, okay? And if the cost at this extended point is even better than the cost at the reflected point, then we will go ahead and just accept E as our kind of our best point, okay? So we will replace W with E. So this E will be the best point, U is the second best, and V is our worst point. And then we would check for convergence, okay? On the other hand, if we move towards to E, and it turns out E is not better than the reflected point, right? So R is better. Remember, R is better than U, and that's why we wanted to keep going in this direction. We wanted to just see if we could push our luck a little bit. But it turns out E is worse than R, Okay, then we would replace W with R. Okay, and then our triangle will be UVR. V is again our worst point, and our triangle would be UV and R. Okay, so that's we do the extension, but that's only if the reflected point is better than our best performing point. Now, students have asked, like, well, if E is even better, why don't you keep pushing your luck, right? And technically, you could have another algorithm that just kind of keeps pushing its luck and keeps going in this direction towards the extended point until it runs out. But that's not how the nelder-mead algorithm is currently written. It just says, okay, if the reflected point is better than you, push your luck a little bit and try out the extended point, and then kind of stop there. What do we do if we do our reflected point and it is not better than V? Okay, so if you check steps 2 and the reflected point is not better than U or V, even if it's better than W, okay, you still wouldn't take the reflected point, okay? Because if you do the reflected point, if U and B still perform better than R, it would be pointless to accept this because R would be our worst performing point, and then what would the next step be? We would reflect it and we'd end up back at W, okay? So if we reflect it and the reflected point is not better than U or V, then we try out two contracted points, okay? We are going to try out CI, contracted on the inside, and we have CO, which is the outside contracted point. And basically, CI is halfway from between W and the midpoint, and CO is halfway between the midpoint and R. Or you could think of CI as being 1/4 of the way from W to R, and CO is about 3/4 of the way between W and R. Okay, so these are our two kind of contracted locations, and we evaluate the function at both of these contracted locations, and we take, if either of these points perform better than V, we will accept it, all right? And if both of them perform better than V, then we will take the better performing point, okay? So we do that, okay? So basically, when we replace, if we start off with U, V, and W, V being our second best point, whatever we contract has to become the new second best, at least second best or best performing point. It cannot, the point that you accept, you don't want it ever to be, still your worst performing point, okay? And if you accept that, then you go to step 6 for convergence, okay? And then the last one is if you've done everything, okay, and none of them outperform V, okay? All right, then in that case, so again, if we have U, V, and W, and we checked the reflection, we checked the contracted points, and none of them outperform V, okay, and U is, our best performing point, what we do is we try shrinking the entire simplex towards U, okay? So we would shrink U, we would move V towards U by, picking a point halfway between U and V. That would be V prime, and we would replace W with W prime by moving towards U. Because right now, U is our best performing point, and we tried all of these other kind of locations, and none of them were better. Or none of them outperformed V, so we're going to go ahead and just kind of shrink the simplex towards that best performing point. Okay, and then again check for convergence. So that's what we do. Checking for convergence is basically, should we stop the program or should we keep running iterations of this? And one is you can kind of check, because you have the value of the function at all three kind of corners of the vertex, right? You can say, all right, basically is the difference between the max and the min less than some value. You can also check for the standard deviation of those kind of locations, and if basically the variance between U, V, and W end up being really small, the amount of difference between U and V and W is very small, you can say, okay, we have reached some kind of optimum solution, all right, that there's not really much of a difference between these three locations here. Okay, let me go ahead and give you, I'll go ahead and give you your first two view quiz answers, which are the letters A and B. A and B are your first two view quiz answers, A and B. Okay, and I made this little animated video for, I guess there's a commercial that we got to endure here. I made an animated video showing the nelder mead kind of algorithm here. Yeah, I know I have these videos posted on YouTube. My channel is not monetized. It's just YouTube plays ads anyway. So, okay. So anyway, this is the function that we're gonna try to optimize. And so, I plotted contour lines, and so we can see that the local minimum is somewhere around here, right? We can kind of see that this is going to be our local minimum, and I guess I will. I'll do commentary in the beginning, and then we'll replay the animation without my commentary at full speed. Okay, so we're going to start off, and this is going to be my starting simplex. Okay, my starting simplex is just these triangles. So I started off at 0, 0, and then I just went +1 in the x direction and +1 in the y direction. Okay, so this is my starting simplex, and so what I'm going to do first thing is I'm going to reflect it. Okay, so I reflect the worst performing point, and I hope we can kind of see that this is the worst performing point. The difference between this and this is not huge, but this is worse performing than this. This is our best performing point. And so we reflect it, and what do? We ask, is this better than this point? It is. Okay, it's better than our second best point. It's actually better than our best performing point, okay, and we can see that because it's below this contour line, all right? And so now this is our new best performing point. So what are we going to do? We're going to try an extension. Okay, we're going to say, well, we're moving in the right direction. Let's try an extension. So it extends it, and you know what? We're moving in the right direction. This one's even better than this. Okay, so we're going to go ahead and accept this point as the replacement for W. Okay, so this point will be accepted. This is my new simplex here. Okay. What is the worst performing point now? This is now my worst performing point. I'm going to try reflecting it first, okay? So I try reflecting it, and then I say, okay, is my reflected point better than my second worst point? It is. Is it better than my best performing point? And can you see? The best performing point is inside this contour line, but this one is not within that contour line. So this is not better than this. So what do? We reflected it. It's our new second best performing point. So we're just going to go ahead and accept the reflection. We are not going to try an extension. So we accept that. Okay, this is my worst performing point. I'm going to try a reflection. Okay, and this performs better than anything. Okay, and so because it performs better than our best performing point, we're going to try an extension. Okay, and when I try the extension, we go, oh, you know what? The extension is not better than the reflection. So after trying out the extension, we will say, we're going to accept the reflection, okay? And so to show the accepted point, I've colored in green, right? So we accept our reflection. What's our worst performing point? This is our worst one. So we're going to try the reflection, okay? The reflection is, what do we do with the reflection? It is better than our second best performing point. Okay, it is not better than our best performing point, so we're going to just accept the reflection. Okay, this is my worst performing point. I'm going to try a reflection. Okay, the reflection, it's a little bit hard to tell. Is this better than this point or not? I'm not sure. If it is better, then we would accept it. But if it's not better, and I would have to ask the computer to see if this is better than this point or not, we will then try a contraction. So let's see. It is better, so we accept it, okay? Because it's not better than our best performing point. We would not try an extension, okay? So so far we've just been doing reflections and extensions, and it's kind of gotten towards this middle zone-ish, okay? And now you'll start to see contractions happening, okay? So what's our worst performing point, okay? Right now this is our worst performing point, okay? And we can see if I reflect it, this like ends up worse, okay? This is not better than this point or this point, okay? So because this is no longer better than this point or this point, now we try out a contraction, okay? So we're gonna try out two contracted points, the inner contracted and the outer contracted, okay? And we evaluate the function at both of these contracted points. Which one's the better performing contracted point? This one's the best one, okay? So we're gonna accept this one. And our triangle contracts a little bit, okay? This is now our worst performing point. We're going to reflect it, okay? And we can say, okay, yeah, you know what? This is not any better than this or this. So we're gonna try out the contracted locations, okay? Which one's better? This one's the best performing point of the contracted location. So this is gonna be what we accept, and that's our triangle. And we kind of keep going, and you can see that contracting starts to shrink our simplex towards the center here. So I'm gonna reflect this. How does that do? That's not good. So we try out these contracted points, and we can see this is the best one. So we're gonna accept that one. And then we reflect this. Again, no good, so we try out our contracted points. That one's better. And so we can see, you know, this is starting to go. So we contract again. And at this point, I no longer have contour lines, so I'm gonna just kind of let the algorithm keep running. And you can see that it kind of, so it's reflecting, and it tries contracting, and it tries, you know, contracting, and then, so I guess this is where it runs out. But let me go ahead and just run the animation at full speed. So reflect, extend, take the extension, reflect, accept the reflection, reflect, extend, take the reflection, reflect, take the reflection, reflect, accept the reflection, reflect, contract, take the contracted point, reflect and contract again, take the contracted point, and this is kind of how the Nelder-Mead algorithm keeps running. It just keeps testing out these different points, and it says, okay, which one kind of performs the best here, right? It takes, you know, the contracted points and says, oh, that's good. And so, okay, and then yeah, so this would shrink even further. That would be how that works there, okay? So let's see. So that's my animated demo. All right, and so R has this function optim, okay? And do I want to show you how optim works? Okay, so you can read about general purpose optimization. And basically, you give it some initial values to be optimized over. You give it the name of a function, and then we ask the algorithm to kind of search for the kind of best performing location. So let's just take a look at this function from Monday's lecture. And what was the algorithm that we wanted to do, or not the algorithm? I forgot. Coordinate descent. All right, so the function, we have this function g, which is x squared minus 2x minus 0.5xy plus 2.5 y squared. And we went to Wolfram Alpha. And we said, find the minimum of this function. All right, and it says, okay, this is the location, 40 over 39 plus for x and 4 over 39 for y. Okay, so let's go ahead and we will, so this is our function, and we are going to optimize this. And so I'm going to just start at some arbitrary location, All right, so I'll just say starting is going to be, I'm going to just put in 0, 0 for my starting location. Okay, and then I'm going to ask optim to do, using our starting location, our par being initial values for our starting location, and then the name of the function that I want to optimize is going to be g. And by default, it's going to use nelder mead method, and so, oh, why did that not work? Let me see. R equals this. Oh, I'm sorry. Okay, I forgot. Okay, so my function is a function of xy. What I actually have to do is I have to rewrite my function, okay, so that it is a function of x, of basically just one set of parameters, okay, and basically I'm going to say x is going to be the first parameter, and y is going to be the second parameter. Okay, sorry. All right, now this will work. All right, so the function can only take in one object. It's a function of x and y, but it's one object. It's a single vector, and I have to kind of split that up. So I'm going to just say x is the first parameter and y is the second parameter. Okay, so this is now this. Okay, so now I can do optim starting on g, and it says kind of our value is 1.0256, and the y is 0.10256. And what is the value? The optimal value is 40 over 39. How does that compare? 40 over 39. Yeah, seems like it did a good job of finding that optimal location. Okay, and that's how you would use something like optim. And optim can accept higher dimensional functions. You just have to, again, you say function of par, and then you kind of split up par into all the different pieces in your function. Okay, and all it does is it just kind of plugs in values and just says, hey, what kind of values can I do to par until it finds the proper values there. Okay. All right, I'll give you your last view quiz answer, which is the letter C, C as in cat. And again, we'll just end a little bit early for today's lecture. I hope that's all right. So we'll call it a day here. Have a great rest of your day. We'll see you on Friday.